Welcome back, and in this video we're going to be doing the first problem about heat exchangers. So this is really what all the class about thermodynamics is about. What is a heat exchanger? Think about it as a heat exchanger any system that is used for cool or heat any other fluid. So the most typical probably will be this one. Let's say you have a hot fluid going on the inside and you want to cool it, so you can run throughout the outside tube a cooling liquid to cool this liquid over here. So we have two types of system of these ones. One will be to have the flow of the cooling liquid going on the opposite direction as the one of the liquid that is inside. That's what is known as the counterflow heat exchanger. The other one is when both flows are going on the same direction, and this is what is known as a parallel flow heat exchanger. This is more about like you can have the fluid and maybe you can just have air going through this. So this is more like the radiator of your car, okay? Or it's a combination. You have water that goes to the engine, the water gets heated up by the heat of the engine, then the waters go through the radiator and the radiator is cooled down by the air of the fan of the outside air, okay? So these heat exchangers have applications in every single aspect of engineering. Alright, so the first problem we're going to be doing, the sample problem, is basically this one. So let's say we have a steam. Steam enters through this tube over here, and then it's going to exit this one. And here the water, you see the cooling water, starts at 20 degrees, so it's going to, heat is going to come from this side, so the water is going to heat up, okay? So basically, if you go through the problem, they give you all the data. You know the incoming pressure, the incoming mixture. So some of this is steam, some of this is liquid, and then at the exit should be condensate. Everything should be on the liquid state, and then here the water remains on the same state, but initially it's at 20 degrees, and then exits at 35 degrees. So what they're asking you to find is what is the ratio of the mass flow. So this is the mass flow of this steam going on top to this one of the cooling. And then find the energy transfer from the condensing steam to the cooling. So basically what is the amount of heat going from here into the cooling liquid. Okay? So again, this is a problem, but you know I like to do figures. So I'm just going to redo the figure, and that way that will give me time to think about the problem. So if I redo the figure very quick, so basically let's see what we have. So we know over here we're gonna have the hot fluid. So let's call this 1, 2. We know this is initially steam at P1 equal 0.1 bar, and the mixture is 0.95, and then P2 equals P1, T2 equal to 45 degrees Celsius. And now we have the cooling. That goes on the opposite direction. That is the reason why this is known as a counterflow. So this will be 3, this will be 4. You know T3 is 20 degrees Celsius. T4 is 35 degrees Celsius. And let's say the fluid going inside this one will be M12. And this one will be M34. Okay. Alright, so once we have this might not be 100% necessary, but it's always a good habit to do this figure over here. So TV or PV. In this case, I'm using the TV because they tell us there is a constant pressure in both cases. So do something like this. So let's say P1 equal P2. Okay, and we know it's steam, so we know we should be somewhere, no, sorry. P1 over here is steam, so we know we're going to be somewhere over here. X1, V1 of H1, and so on. Okay? Alright, so the first thing we notice is that this one is what type of system? This is a system in which we have mass flowing. So we know this will be either a control volume problem or what I like to call a open system. So for this control volume that we specify, so for the specified control volume, what do we have? Heat transfer minus power to control volume plus whatever is going in, which is what? M12 H1. What else is going inside the system? Plus M dot 34 H3. What is coming out? M12 H2 plus M34 H4. So obviously in this problem we are neglecting the kinetic and the potential energy. Alright, so in this problem, do we have any heat going in or outside the system? No. Do you see any work? So again, all the equations need to come from the figures. So now from this equation, we can write M12 H1 minus H2 equal to M34 H4 minus H3. Okay, so we find the ratio. Let's do this one over here. M34 over M12 will be equal to what? So I move this one down here, so it will be equal to H1 minus H2 divided by H4 minus H3. Okay, and here we go from here, I'm guessing to here. So this will be for the hot, for the steam or the hot liquid. Alright, so now what we need to do is find H1, H2, H3, H4. So we know the substance we are dealing is basically water. So for H1, what is the state? So we know it's going to be a mixture. So what does that mean? That we need to go to the table for mixtures. And that will be table A5. So table A5, we know the pressure. So we have the pressure is equal to 0.1 bar, which is basically the same as 10 kilopascals, because we know that 1 bar is 100 kilopascals. So at 10 kilopascals, let me zoom in. At 10 kilopascals, since it's a mixer, we need to find HF, which would be 191.81, H gas 2583.9, and HFG is 2392.1. Okay, so let me just write that information on the page. So basically I have from table A5 at P equal 0.1 bar, which is equivalent to 10 kilopascals. We have H fluid to be equal to 191.81. H gas is equal to 2583.9, and HFG, which is just the difference between these two, is 2392.1, and all this will be kilojoules per kilogram. So once we have that information, we know that H1 will be equal to what? H fluid plus X1 H FG. So this will be equal to what? 191.81 plus 0.95, 2392.1. If you do the numerical application, you find that H1 is 2464.305 kilojoules per kilogram. Okay, and again, how do we know which table we need to use? Because we use that figure. So now we have state 2. So this is the tricky one. So H2, if you remember, there's a video about it. When everything is saturated liquid on this side, generally there is no table. But we discussed that in that case, the properties almost do not change in function of the pressure, but only in function of the temperature. So do you remember, once a property is in one state, the value should not change that much. Okay? So since here we know that it's not going to change much along the line of pressure, but it's going to change in function of the temperature. Okay? So we need to go then to the table over here for the temperature. So what will be that table? So for table A2, that would be, we use table A5, so it's probably table A4 at, there we go. So basically we go to table A4 at what? We need to look at the temperature. So for H2 we need to look at 45 degrees Celsius. What do we have? 45 degrees Celsius. This time we are only interested about the H fluid, which is 188.44. So we have H2 equal H fluid equal to 188.44 kilojoules per kilogram. Okay, now let's see what happened for 3 and 4. So 3 and 4 is basically something similar, because this time we know the temperatures, we know it's constant pressure. So we know one would be, let's say, at 20, so it could be 3, and then this could be 4. So 20 and 35. But basically it should be the same table. So for H3, same process, table A4 at what temperature? 20 degrees Celsius. H3 will be equal to H fluid, which is equal to what? So at 20, you can see that H fluid is equal to 83.915. 83.915 kilojoules per kilogram. If we do exactly the same thing for H4, table A4, at this time what temperature? 35 degrees Celsius. We find that H4 equal to H fluid, and that will be equal to what? 35, 146.64. 146.64 kilojoules per kilogram. Okay, so basically now we have all the information that we need in order to calculate the ratio from that equation. So let me just rewrite the same equation on the other side. So recalling that M 34 over M 12 equal to H1 minus H2 divided by H4 minus H3. What do we have? We're going to have that 2,464.305 minus 188.44 divided by H4, which is 146.64 minus 83.915. We'll find that the ratio M over M 12 to be equal to 36.28. So basically, what does that mean? Is that the mass flow of the cooling is 36.28 times the one of the hot fluid. Alright? So now in the second part, we need to find out how much heat is actually transferred from this side into this side. So now what's important is that we're just going to take the top part of the system, which means the one of the hot fluid, where we have 1 and 2. So now we're going to isolate this part, so this will be our control volume. And now what's going to happen is that the fluid of this one, we know the heat is going to go from the hot fluid to the cooling fluid, which is the water. Okay, so we know some heat transfer is going to go out to the other fluid, which is over here, and this will be our control volume. So basically it's the same process before. You do the figure. Now what is the equation we're going to apply? For the above control volume, what do we have? Q minus power of the control volume plus M12 H1. So this time we only have this one. And what is coming out? M12 H2. On the figure we have no power anywhere. Okay, so we need to solve for the Q. Will be equal to what? M12 H2 minus H1. But we need to find this result in kilojoules per kilogram. So basically it means Q over M12 equal to H2 minus H1. So if we solve, what do we have? Q12 over M12. Really, the units of time cancel out, so we don't need the dot. Should be equal to what? So the dot disappears, because this will be what? Kilojoules per second, and this will be what? Kilograms per second. Okay, so this will cancel out. So we have H2, which was equal to what? Let me check on 188.44 minus H1 2464.305. So that will be it. And this is equal to negative 2,275.87 kilojoules per kilogram. And this will be the final answer. So once again, what's the meaning of the negative value? If you remember, in this, on the sign convention we are using, heat going in is positive, heat coming out is negative, work done by the system is positive, work done on the system is negative. So the negative sign means that is heat coming out of the system. Okay, so that would be the end of this problem. Thank you for your attention.